video. It is me, Unsweetened Uranium, and I hope you're all having a good day. Alright, so today we're going to be talking about alkynes. So this is another word you're going to be seeing a lot in Organic Chemistry 1. An alkyne, essentially, as we've gone over alkanes, right? So carbon-carbon single bond. Then we have alkenes, and now we have a carbon-carbon triple bond. An alkyne. So when you hear alkyne, that's what it means. All right. So here I have two examples. All right. This first one here, you'll notice I put the hydrogen in red. Okay. And then on the second one, I have it in green. And essentially the difference between these two is going to be one is a terminal alkyne and one is an internal alkyne. So if we look at this carbon-carbon triple bond right here, okay, we'll see that on one group has an R group right here, okay, and the other side it has a hydrogen. Okay, if we go down to this one, here's our carbon-carbon triple bond. One side we have an R group, other side a different R. Well, it's the same. We have another R group. Okay, right? Methyl group here, right? So this one is terminal because you want to think about it as on the end there's a hydrogen. There's a terminal hydrogen right here on the end. Okay, over here we don't have one. We don't have any hydrogens on this carbon-carbon triple bond on either side. Okay, so that's where the difference in names come from. So one's an internal, right? You want to think about this triple bond as being sandwiched in between. And then this one, on the triple bond, we have a hydrogen on this side. Let's talk about this triple bond. So you've definitely noticed that there's something strange going on here, right? Because we have a triple bond. We usually see single bonds, right? A sigma bond, a pi bond. But now we're seeing a triple bond. So let's think about what's going on here. So this is going to be acetylene gas, right? And I'm going to drop a link to a cool video you can watch about acetylene gas. But we have a carbon here, hydrogen, hydrogen. Okay, so this is C2H2. All right, that's the formula we have. So we have a sigma bond here, and then we have a sigma bond between these two carbon atoms. Another sigma bond here between the carbon and the hydrogen. But now look at these pi bonds. Okay, so we have a pi bond here, right? And then we have a pi bond here. And what I want you to notice about these pi bonds is they're all perpendicular to each other. If you notice, right, we have 9 degrees there, 9 degrees there, 9 degrees there, 9 degrees there, right? They're perpendicular. So that's important to keep an eye out for. In case you have to draw this on an exam, right? You want to draw it perpendicular as best as you can, right? And the reason these are going to be reactive is because if you think about this, right, just kind of from a logical point of view, we have a lot of electrons here now. So we have a close proximity of electrons that pretty much it's going to create a molecule that's less stable, right? So if it's less stable, it's going to be more reactive. So speaking of reactivity, let's do some reactions next. First example reaction. So this one might be a little difficult at first, okay? Might be a little challenging, but let's give it a try. So let's say we start with something, right? We're going to start with a terminal alkyne, okay? So we're going to start with this, right? Terminal alkyne, hydrogen on the end. And I want you guys to realize that because the hybridization of this carbon is sp and not sp2, it's actually going to have an easier time getting rid of this, being deprotonated, okay? It's going to have an easier time deprotonating because those electrons will have more s character, they'll be closer to nucleus, they're more stable. So if I took a terminal alkyne and I mixed it with a strong base, let's use sodium azide. So sodium, right, a positive charge. Azide is going to have an NH2, right? It's minus, so we're going to have those electrons. And what's going to happen here is these electrons are going to deprotonate our molecule. These electrons are going to go onto that carbon atom, and what you're going to get is you're going to get this. Okay, and then you're going to have the sodium ion is going to be right. So this is acetylene ion, and over here, well, if we had NH2 minus and we had a hydrogen on there, right, then we're gonna make ammonia, right? That's all that's gonna happen there. So we're gonna have ammonia. We can leave it out, but it would be over here in your reaction. And now we just made a strong nucleophile. If you look at this, we made a strong nucleophile there. And we're actually gonna see that it can attack another molecule. So let me just think of one off the top of my head. Let's do this. Let's do 1 second. Let's undo that. Let's react it with, draw a reaction arrow. Let's do H3. All right. So we draw this out. It's okay. Reacting this. So we're gonna have a little SN2 backside displacement occur. And don't worry, we'll do a whole video on SN2 reactions. I'm gonna go here. Iodine's going to be kicked off. So for our product, we went from a terminal alkyne to a internal alkyne. So this is just to show you that this is a certain way they can react, right? So if we have a terminal alkyne and say we want to add this to something or add something to it, right? Depends which way you want to think about it. We can change it into acetylene ion, okay? And then we can use this, because now we have a strong nucleophile. We can use that to attack something with a good leaving group, for example, right? That's one way to think about these. Let's do another one. Delete all that. Let's do another reaction. So let's do acetic gas. Let's practice what we just learned. Okay, and first step, all right, so we have our sodium azide, okay, right there. And then we're also going to add, let's see, I gotta think of a, sorry, sodium amine, not sodium azide. Azide would be the N3, right? So sodium amide. Um, let's add second one. Let's do this. I'm gonna draw it out. Get used to seeing what's going on. So it's primary. So SN2 should still work. All right, let's get started. So the first step here, all right, we're going to deprotonate. We went over that. So I'm going to skip ahead. Okay, right, so negative charge, this means gonna, right, because we had two here, one of these is gonna take this off here. That's how we get to this. Okay, now our next step is, look at this, we have a good leaving group right here, bromine, good leaving group. So if I add my 1-bromobutane, should get by SN2, should get this 1, 2, 3, 4. Always check to make sure you have the right amount of carbons. 1, 2, 3, 4. 1, 2, 3, 4. Okay, but you might notice, okay, well, a terminal here, I still have a terminal hydrogen here. So this would actually react twice, right? Because this is going to occur, okay, and we're going to still have some of this in our flask, right? We had this first, and we had that, but we're still going to have this run around. So it's actually going to react again. Okay, so what's going to happen here is we're going to react it again. Okay, so if you did this in two separate steps, then you could change this. Okay, I know I wrote two separate steps, but imagine we repeat it. Okay, so we're going to run through it again. But say on this next one, you want to add a different group. Let's do that. So let's use our sodium amide, not sodium azide. Let's use our sodium amide to deprotonate. Okay, so we have it here, sodium amide. But now I want to add a different group. Let's add something a little strange. Yeah, let's add this. We'll use iodine. So, still primary, so it still should be good for SN2. Little bulkier, so it might be a little more difficult than this because of steric hindrance. But we're still going to give it a whirl. So first step would be deprotonate. So now we have our new, I'm going to draw it over here. So now we have our new, and I'm going to reverse it. Okay, so now 1, 2, 4. It's a little crunched over there. And now, strong nucleophile, and we have a leaving group on our other molecule. So this is going to SN2, kick off the leaving group. Those electrons are going to go on iodine, right? Good leaving group. It's large. Can really stabilize that negative charge well. And what's going to happen here is we're going to make an internal alkyne with two different groups. That's a long, my bad. That's a long bond, but 2, 3, 4, 1, 2, 3, 4. Okay, so this would be the product. All right, any questions on that or any confusion, drop a comment below. Remember, it's sodium amide, not sodium azide. We'll use sodium azide down the road. But all right, let's do another reaction. We'll do two more. Okay, this next one, let's do. So we know how to make this, right? Use a strong base to deprotonate it. So allow us to use that kind of as a starting material for this. Okay, so pretend we already added our NH2, and we'll do a more formal one next, but pretend we just added sodium amide. Okay, so we just created this, and let's say I have a ketone over here. Okay, so this is a carbonyl over here. It's a carbon-oxygen carbonyl. And you're going to learn to react it because it has a negative end and a slightly positive end over here. So what's actually going to happen is this lone pair will attack the ketone here. Okay, these electrons that were in the pi bond are going to go up onto this oxygen atom. So we're going to end up with something that looks like this. 3. Now we have a bond to this, what was our ketone. Okay, so those are our groups, our prime. Actually, I'm going to put this so we don't get confused. Okay, now look. Oh, 1, 2, 3, 4, 5, 6. You recognize it's going to have a negative charge now. Okay, and what we can do after that is just add a little bit of acid, right? Doesn't matter. Just add some acid to that, and now this is our product, right? So we're actually going to have an alcohol in the end. We're going to have an alcohol down on the end. All right. So our floppy, our prime, and this is what you're going to get. Okay. So we started once again, terminal alkyne, deprotonated it, sodium amide. Then we attacked this ketone. All right. And then we formed this alcohol. So if you wanted to say have hydrogens here, you could use an aldehyde here, or you could just, so you could have an aldehyde, right, formaldehyde, which would have hydrogens on both sides if you wanted both these to be hydrogen. So, a bunch of different possibilities here. All right. I'm going to do another one, and this time I want you guys to try it on your own before you watch how I do it. So I'm going to draw out the reaction. All right, so let's say we have this. Okay. All right. First, see, this was an exam. Predict the products. Sodium amide. Second, let's add. Let's add. Oh, you guys might not know that yet. Okay, let's just do acetone, and then third step. All right. Oh, acid. Okay, so take a moment, try this out. All right, let's get started. So, terminal alkyne here. You know the first step is this amide is going to deprotonate. Those electrons are going to go onto here. Okay, so let's start with that. All right, next step. Now we have this plus our acetone. Okay, so you see that you should recognize that carbonyl group. These electrons are going to attack right there. Those electrons are going to go onto the oxygen atom. Okay, and we're going to get a charged intermediate. Okay, 2, 3, carbon. Going to be attached to this, right? And these are just methyl groups now, not R like the last example. Okay, and now we have our charge intermediate, negative charge, and then once you add the acid, pretty simple, right? These electrons are going to attack the protons we have flying around. There we go, and we have this 2, 3 carbon, this, okay, with the 2 methyl groups, all right, and our alcohol down here. All right, so that's what you should have got for an answer. If you did it differently or have any questions, comments, or concerns, drop it in the comments. All right, we'll do one more. one more. Okay, let's do. Let's see, I'm going to give you guys a challenge on this one. What would happen if I had. Once again, I want you to try this before you watch how I did it. Let's do cyclohexanone. Okay, so ketone carbonyl right there. And let's just start this time with our sodium acetylide ion. 1, 2, 3. Let's do this. Okay, and then acid workup at the end. H3 plus. Okay, so try this. All right, let's get started. What you have to recognize is that carbonyl group, the carbon that's attached to that oxygen, has a slight positive charge. So what's actually going to happen in this case is, change the color. These electrons are going to attack right here because of the slight positive charge. Right, so we have a strong nucleophile, right? And electrophile over here, right? This electrophile, can't tell you if it's necessarily strong or not, but I do know it's electrophile. But we have a strong nucleophile, so it's going to react with the electrophile. And what's going to happen is we're going to create a bond. Okay. And, well, what did we forget? I hope you did forget that we have to kick those electrons around the pi bond, right? Because we can't overload this carbon. We don't want to get a Texas carbon, right? 5 bonds of carbon, no good. So we have to take those electrons around the pi bond, throw them onto this oxygen atom. So then we get this, okay? And for our next step, we're going to hydrogen, okay? And it's going to attack that. And for our product, we would expect this alcohol group there, and another group was added, right? We added this, and you'll notice if you want to use this to attach it to something else, you could depronate, right? And then react it with something else. Okay, so any questions about this? Let me know. Obviously, you want to, on exam, you want to do this by step. So I would show this as a step, draw an arrow to this step, show this as a step, draw an arrow to the product. Okay, don't try to do everything in one step. All right, so unsweeten uranium out and have a good one.